right now. All right, so thanks a lot for being here. My name is Edoardo Carlesi. Please don't do this again. And this is what I'm going to talk about. So how did we get to that point? How did we get to that song? And it turns out that if you want to know the story behind Hello World, you need to go to the beginning of the universe, more or less, because that's where the whole journey starts. And I'm going to share with you a few thoughts and experiences and ideas about different topics, including the band that they are here with me. I hope you have seen our show today, this morning. I don't know if any one of you was missing, but what you've seen now, it's the official video of the song, the first song that we played this morning. So let me start with a short outline of the talk. So as I said, we need to start the journey from the beginning of the universe. It's going to be a long journey, but we only have 44 minutes, so we'll compress it and make sure we'll make it within the allowed boundaries of time. And then we'll talk a little bit about the world, so how satellites and can help us observing the Earth, and what we can learn from that, and how we can apply machine learning to the Earth observation. So how we can analyze pictures of that are taken from space, and how we can make sense of those using machine learning and deep learning. And then I will end with some funny stories and some more insights about some of what we did as a band, Nanowar Of Steel. So Uranus, one of our songs, HelloWorld.java, and some upcoming things as well. So as I said, we need to start with the universe. Why? Because that was the topic of my PhD, and that's how I got into programming. And basically, it turns out that if you want to study the universe, you really need to know a lot about computers. Because what you want to do is to make sense of the Big Bang, so of everything that happens between the Big Bang that is here. So what you have here on the x-axis is time, and every slice on the y-axis is a picture of the universe, a two-dimensional picture of the universe at different times. And you want to be able to start from here, so from the Big Bang, up to our days, where we are able to throw satellites into space and take pictures of the universe. And if you want to do this, you need to run simulations, because you need to start from the initial conditions of the universe, from the Big Bang, where you have this huge amount of gas that collapses and starts forming stars, and then eventually galaxies, and galaxies merge, and they form clusters of galaxies, and so on and so forth, and they evolve into what we see nowadays. And as I said, this is a very computationally intensive task, because you have very different scales that you need to take into account at the same time. So the universe contains things like the Earth, that is part of a solar system, that in turn it's part of our solar interstellar neighborhood, that is part of the Milky Way galaxies. And again, everything here you see, maybe you don't see that so clearly, but you have a huge difference in scale. So you have billions of stars within the Milky Way, so you have potential billions of Earths as well. But again, the Milky Way galaxies, it's not the last thing. It's a part of a local galactic group, that is part of a Virgo supercluster, that is part of a local supercluster, that is part of what we see is the observable universe, and there's probably much more going beyond that. And so when you run simulations, actually, you really need to take into account all these elements that happen at different scales. So you really need billions of particles, and you know that if you have billions of particles in a simulation, you need to have lots and lots of memory, because every particle, of course, has its own float numbers that are associated to it. They have velocities, they have densities, they have mass, they have positions, and you need to keep track of all of those. And so when you simulate the universe from the start, you want to see how these galaxies, how these stars within galaxies form. And so you need, again, very powerful machines. And what you usually do is you run that on HPC clusters. So usually you have to have some very efficient programming language. Usually it's either C or C++, and you need to parallelize it. So you have, at least what this was back then, now I don't know if things changed in recent years, but up to 5 years ago, the standard was running C and C++ on MPI and OpenMP. So it means that you needed to run and write the programs that could be parallelized. So you could split, basically, every part of your box. So this is how your box looks like at the beginning. It's like a part of the universe. You see it's very homogeneous. And you give basically each task, each processor analyzes a subset of this box. And so you need to parallelize it with OpenMP and MPI. And so what you see here is the different phases of the evolution of the universe, going back, as I said, from a very homogeneous phase where you have the universe is filled with gas, and then you have small fluctuations, and the fluctuations, of course, when you have gravity, if you have some more matter in one point and some less matter in another point, you will see that these differences grow exponentially. So the part with more matter will have more gravity and will attract more matter from the part of the universe with less matter, and this will trigger the formation of stars and galaxies. And you see that all these stars and galaxies, they coalesce and they form these filaments. And you see these filaments become thinner and thinner and more dense. and you also see the formation of voids. And again, what you're doing here is basically just taking the laws of gravity, spreading them across thousands and thousands of cores, and making these tasks on your computer, on a very efficient computer, talk to each other, and in the end, you end up with a picture that looks like the universe today. Right, so you have something that more or less in a statistical sense looks like the universe today. And this is what I've been doing for many years, and this is what got me into programming. So, at some point I realized that when you have to do analysis on a huge amount of data, eventually you need to turn to machine learning. You need to turn to very advanced techniques. And this was my first work on the topic. And the idea here is that when you have a simulation, of course, and you have a galaxy within a simulated environment, you have all the variables about the galaxy, of course, because this galaxy lives in your computer. So what you have when you have a simulation, it's something fake, but you know everything about it. And so we thought that we could take some of the properties that we can actually observe, because it turns out the universe, even the nearby universe, is not so easy to observe. So we cannot really see everything we want. For example, still nowadays, it's very hard to measure the mass of the Milky Way. I mean, we live within the Milky Way, but it's very hard to measure its mass. There's a lot of uncertainty. You can measure the number of stars, but then you cannot really measure how much gas is in there. And so what you want to do, basically, when you have a large amount of simulations, is to find some features that relate the features that are not directly observable to those that you can observe. And if you do that with machine learning, you find that you can do magic, basically, because machine learning is I don't know if any of you uses machine learning in its routine daily. Just okay, I've seen a couple of heads. No, that's good. So machine learning, you basically need to reconstruct nonlinear relationships between variables. And so what we did in this work was basically to reconstruct the mass of the Milky Way from a set of observable variables, like the velocity of stars within the Milky Way, the velocity of the galaxies around the Milky Way, and others. And we found some nice estimates. But then at this point, that's when I got bored of galaxies and space, and I decided that you can actually turn telescopes to the wrong direction. So as an astrophysicist, if you take a telescope and look at the Earth, for me, is the wrong direction. That's what I've been taught. Like, telescopes are in space because they need to observe the space, not to observe what happens on this very boring place called Earth. But I was wrong, because actually you can do cool stuff with that. And the idea is that you can analyze, actually, there are many missions that do exactly that, from missions from ESA, from NASA. And this morning there was exactly a talk about this, how to use NASA data, how can you explore them. And what these missions do, for example, what the mission Sentinel that is by the European Space Agency does, is it sends two satellites into space. These satellites rotate around the Earth, and they take pictures of the Earth at constant times. And the funny thing, I mean, the most interesting thing about these pictures is that they're not normal pictures. So normal pictures that we take with our cameras are RGB pictures that we see with our eyes. So we are all used to seeing RGB images, like normal images. But these satellites have this so-called multispectral imaging sensor, which is basically a sensor that takes pictures into parts of the electromagnetic spectrum that we do not see with our own eyes. So they take pictures, like, again, if you think about an RGB image, I don't know if you're familiar with computer vision or processing of images, but usually in computers you have three layers. So one is for the R, one is for the G, and one is for the blue, red, green, and blue layers. And you combine them and you get the normal colors. Now you have to think that you can extend this beyond only these three colors, but you can get to 11, actually 12 bands. So these are the visible ones, the ones that you see here, the blue, the green, and the red. But if you take the full electromagnetic spectrum, you get a lot of more information. So you can get a lot of other bands. So you get near infrared, shortwave infrared, narrow infrared, and so on and so forth. You can get also the ultraviolet. And why is this important? This is important because, of course, the Earth is full of different substances, and every substance interacts with the electromagnetic spectrum that you see here with different frequencies and different properties. So every time the light of the sun hits the Earth, you trigger a reaction between the light of the sun and what is there on the crust of the Earth, on the surface of the Earth. And depending on the color or the frequency that you're looking at, you might be seeing different things. Now, one problem with this is that you might have problems related to the atmosphere. So if there are clouds, if there is a storm, if there is a lot of humidity, the light that is coming from the sun will be distorted. So you need to correct for that. But apart from that, of course, when you have multispectral imagery, if you look at just the RGB part, you already know what you're talking about. You can see the image, and at least you can recognize what's happening. Now, let me show you just an example. This is what you see here is a picture of Venice in the RGB. So this is a normal colored picture of Venice, and this is what you see in the near infrared. So this is the near infrared, just one band. It's projected into the black and white space because it's one-dimensional. This is three-dimensional, so we can, because there's red, green, and blue superposed, so we can see the full coloring of this. But again, you can imagine that for each band, each one of the 12 bands, you have a picture like this, and then you can stack them. You can make combinations of these bands, and it turns out that these combinations give us a lot of information. So, for example, there are some indices. They are called spectral indices. And these spectral indices are, for example, the NDVI, Normalized Difference Vegetation Index. This is just an algebraic operation where you take, again, this, when I say near, so this near infrared, this picture, and you subtract just the red value to it, and then you divide by the sum of the two. And this NDVI is very closely related to chlorophyll. So this quantity, when you take the pictures of the Earth, it's very close. It's a very good tracer of the presence of chlorophyll. It's a very good tracer of the health of the vegetation on the surface of the Earth. So this is a very important thing to keep in mind. You can do the same for water. If you want to take pictures and detect the presence of water, you can use this combination of bands. And same thing, if you want to analyze burned areas on the surface of the Earth, you can do this other kind of combination. There's a huge number of these kind of things, but I hope you get the idea that it's pretty easy because you just need to download the full stack of all the bands, and you can play with them, and you get information that are actually very useful because they tell us where the vegetation is, where the water is, and so on and so forth. So there's a lot of, again, I'm just putting here for reference some scripts that you can use to do this kind of analysis. And again, this is, for example, if we take the province of Rome, this is seen in the NDVI, and the darker regions are related to the presence of healthy vegetation, and the clearer one, more towards white, they are related to water in some way, to the absence of vegetation. And same thing you can see in the NDWI. This is again, this is for vegetation, and this is for water index, and you see the water areas are very well highlighted. And this is, for example, useful if you have a flood happening in some region. You can take pictures from space, and you see exactly where the damaged parts are, where the most impact is. And you don't need to go there physically, you can do it from space. So, let me show again another application of this kind of things. This is another kind of color coding projection of the NDVI. So I'm just using a different coloring scheme just to show you that if you take this number that you get from the sum and the difference of these indices of these bands that you get from the satellite missions like Sentinel-2, you can highlight very well. So these are, for example, from -1 to 0, when you get this numerical value, you can highlight. This is the province of Trieste. In northern Italy. You can see the regions with water, you can see the regions that are built, the red ones, you can see the regions with asphalt in gray, and different kinds of vegetation. So these are like the darker one, and the clear one is again, it's like fields, and this is the darker one is for forests, for actual trees. So again, this is just to show you the power of this kind of data. Most of this data is open, so anyone can subscribe and get it from Google Earth Engine, or the Sentinel mission there's a Copernicus hub that offers this data for free. So it's very useful and very powerful. And for example, if you want to see the evolution, this is a project that we worked on with my company that I work for. We analyzed the NDVI. So again, this is, I remind you, this is value of the vegetation. So the higher the value, the healthier the vegetation. And we took a province, this is a municipality of Comitini in Sicily. And you, for example, you can analyze how the trend goes. So how is the vegetation? Of course, you have fluctuations here that are related to seasonality because of course during the summer it will be drier and the winter will be there will be more water and the vegetation will grow more. So this is for a municipality, and you can see the trend is downward sloping. So one of the projects we had was developing this system where we analyzed for different areas of Italy. We could analyze and extract the trend, so the long-term trend, and see whether things were improving or getting worse with time. Now, I don't know if any one of you works with deep learning. Just a couple of words about another kind of application that we did with this kind of imagery. And this is just to show off some deep learning architecture of a neural net. This is a UNet. Again, I don't know if you're familiar with it, but it's just and the name for a kind of neural network where you have the encoding and decoding branches that they are basically do a lot of complicated things with filters and so on and so forth. But the idea is that you want to segment the images, so you want to analyze those images and divide them into constituents. So you want to find within these images where for example, where the vegetation is, where the built area is, where the streets are, where the water is, where the fields are, because you, for example, you want to track whether built areas are increasing in some places. You want to be able to identify, for example, if there are structures built within national parks, if there is some kind of irregularity there, and you can do this all for space. So let me remind you that the great advantage of satellite imagery is that, first of all, it's free, most of it, but it's, again, and the other thing is that it's taken very regularly. So every 5 days, actually, with the Sentinel missions, you have pictures of the same place. So you don't need to send anyone there, you don't need to send drones, you don't need to put sensor, you can see from space, and if you're clever enough to analyze these images, you don't need to, you can do it from Coimbra, so whatever, from wherever you want, just sitting down and analyzing those pictures. Again, this is what I mean by segmentation. This is one for those who are familiar with training. This is the max, so this is the kind of image that we use to train the neural network. This is the original picture of the Earth, and this is what happens when you process the picture through the neural network. So you identify all the areas. So you identify the blue areas with water, the red areas with built, so with buildings and civilian structures. The yellow areas are barren lands, and the green ones are with trees. So again, this is an example of deep learning, but let me talk a little bit more about my latest project, and then I think it's pretty much the last topic, serious topic, so I apologize for being so serious so far. Don't worry, the fun part will come later. This is a fire risk index. So this is a project that we are working on. Again, it mixes satellite imagery with meteorological station data. So what we are doing, we have a two-layer system that in real time analyzes the weather. This is a picture of the province of Catania in Italy. And it produces this, you see that the province is divided into squares. There's a grid, and for each grid we know that we have real-time data that are given by meteorological station. And we can analyze the temperature, the humidity, wind, and other physical parameters that are related to the fires. So we know if there is a very high temperature, very low humidity, and very strong winds, there might be regions that are problematic. They might be subject to the ignition of wildfires. And so the first, I was mentioning, we have a two-layer system. The first system interacts with the APIs. There are some meteorological stations that offer their data for free, and they're open, so we use those to compute the values of, there's a fire risk index. It's a mathematical formula that gives you, on this color coding, a value that goes from very low to higher. I cannot read it now, but anyway, I think you get the idea. So the red parts are those that are more subject, they are more risky. So the idea here is that we can use this free sources to produce this kind of maps. And every time an area within this map goes above a threshold, so for example, if we are above, I don't know, 2, like in this area of red, then we trigger a second part that is based on machine learning that actually goes there and takes the satellite imagery relative to the dangerous region. So we don't need to analyze everything, of course, because if some area is raining or in some area there's not enough temperature, we don't need to analyze what's going on there with the actual satellite imagery. So we don't need to, because as you might guess, like analyzing images is very expensive from a computational point of view, because you need to implement machine learning algorithms, deep learning, and so on and so forth. And even the images themselves, we are talking about gigabytes of data per slab. So these are images that are taken by the satellites. They are divided into slabs. So you need to take those, and you need to take more of those to get some meaningful machine learning algorithm to process it. But anyway, so once you see that your area is in danger, you can call your download the satellite imagery from the APIs of these services that you're subscribing to. And this is, for example, this is a picture of an area where you can apply machine learning algorithms that have been properly trained to tell you where the dry vegetation is, basically, because the dry vegetation is of course, the vegetation that is more risky from a fire point of view. Of course, you need, it's a kind of fuel. So if you are above a certain temperature, then you need some kind of fuel. You have to have the fuel as well. You don't just need temperature to ignite a fire. You also need some fuel to be there. And these machine learning algorithms that we trained tell us exactly where the drier vegetation is. So you can focus exactly just on those areas when you have when you run again into complicated physical conditions from the point of view of humidity and temperature. So this is just to show you how the system works. It's a very standard architecture of microservices. So we have a scheduler that queries the API. So we query the meteo services and satellite services on a constant timing, depending on when they are updated. Meteo services is updated almost real time. We do some pre-processing on those, of course, because satellite data needs to be cleaned, and because of what I told you, for example, for the atmospheric corrections, as was mentioned at the beginning. And of course, you need to get the fire risk, so you need to compute, you need to find out first where the dangerous areas are, and then you would go and trigger the full processing of those areas with the machine learning. And so you store all this data anyways, and then we have some maps that we can use locally. Use Streamlit because I'm lazy. I'm a very bad front-end developer, so I just do everything with Streamlit. So just check out that what's being processed and stored in the database makes some sense. So we can overlap. We can plot these maps on the actual physical maps and see whether there is some mismatch and if everything is running smoothly. Otherwise, we developed some APIs that can be queried from outside, and they return a GeoJSON file that is then can be used by any other application if you fancy. So if we are working with some other companies to implement this, so they are taking our output as input of their systems. But if anyone is interested, then we can. They're closed APIs, but we can talk about that if you're interested. But I think that's it, because that was more or less had nothing to do with what I'm going to talk about now, because now I want to talk to you a little bit about Nanowar Of Steel, about Uranus and HelloWorld.java in particular. And Uranus is a song. We didn't play it today. It's about the planet, but it's also not about the planet. Maybe you can get the joke. I hope you do, without me needing to explain it to you in detail what it's all about. This song, okay, so basically, first, before I talk about Uranus, this is the band. This is how it started. They are there. We are here. This is how it's going a couple of years ago. So we made it a long way forward. I'm pretty happy about this. And again, I was talking about Uranus. It's a song that we released 7 years ago, then we re-released 5 years ago. But to make things short, this is how we looked at on that video. And it's a pretty cool video, so I suggest you check it out. We'll watch a part of it, but the thing is that we went, I'll tell you a funny story about this video. Again, I hope you understand the joke, because the guys that gave us permission to film here, this is an astronomical observatory in Italy, they didn't get the joke at first. So we had an issue, because I was pretty sure that an astrophysicist would be fluent enough in English to understand the joke without me actually explaining that Uranus, there's two meanings of the words. He only got the astrophysical meaning, unfortunately. But anyway, so we were lucky enough to shoot the video and get it done. And by the time we got it done, the guy, actually the director of the observatory said, no, you cannot do the video anymore. So in the end, we found a compromise. We shoot the video and we used all the scenes that we filmed there, but we put that we shoot the video in some other location in Switzerland, that just random place. So well, we went to Switzerland to film, yeah, of course. But it's a cool video, and I think it's nice. I just want to show a piece of that. I like it big. I hope you got the joke. If anyone needs an explanation, you can ask those guys there. I'm pointing at them, so they're also responsible of these very bad jokes. Talking about jokes, this is a joke that went too far, and I'm pointing at the responsible, at the main author of this. He's the Java developer in the band. And this is the repository. I think it's the first GitHub repository of a song, at least, that we know of. At least that it's so successful. This screenshot was taken a few months ago, but we got a lot of stars, shares, rewatch. We got a lot of pull requests and everything. So it was, you've probably seen this. I don't know if any one of you have seen this video before, but anyway, so if you are not subscribing, if you are not started our GitHub repository yet, please do so as soon as possible. We need more stars. We are ignoring everything on this repository anyways, but and again, so the idea is that this song is the first song that is executable song, because the full text lyrics of the song are just Java code written by this guy over there. So, and if you remember the song though, there is a very sad ending to it. There's a note pointer exception. It's very sad because we cannot really execute the full song. It's at some point it crashes. I mean, we're used to that, but it would be nice to fix that. And it turns out we needed some very powerful help. We need some endorsement to fix this issue because, basically you can see this line here. Metal false. If metal is false, then it triggers the call of this function that, it's calling a null string, and it triggers the null pointer. It's a very, very sad and very serious bug, I guess. No one in this room would be able to solve this. So we had to to use IntelliJ, and we got some help from JetBrains. And as we mentioned today already, I think we are the first metal band that is being endorsed by some software factory rather than some Marshall or whatever, like instrument factory. And so we teamed up with JetBrains and IntelliJ and their AI-powered IDE, and we fixed the bug. We're pretty proud to tell you that. And I don't know if you've seen that, but we released a patch of the video. So now it's the first song that has a patch. Now I will show this to you, and I hope you like this patch. It's not working. Oh, why isn't the audio? This is very sad. Demos, yeah. Let me put it from YouTube then. Because you need to see the patch. You need to learn something at this. How to fix Java code problems. So. Patch probably. Okay. So this was the null pointer exception, but you see, instead of using Eclipse IDE, you can use IntelliJ with fix with AI. We wouldn't have been able to solve that without AI. Thank you, IntelliJ, smart AI, because otherwise we wouldn't have been able to show you how the program finishes. So, dove cazzo stavo? Visualizza. Presenta. So, I think, anyways, we got to the end of the talk. I'm just spoiling. Well, we spoiled this morning. There's coming next in death metal, Kotlin song. I hope you enjoyed it, and if you missed it this morning, then it's your fault. But I think that's all for this talk, and thanks for being here. And the talk is finished.